We're back for the final stretch here. What we're going to do is talk about the combined gas or the ideal gas law, and we're also going to talk about Dalton's partial pressures to end this section. What we need to deal with is earlier we talked about pressure, we talked about volume, we talked about temperature, and we compared those in two situations, in a syringe, in a barrel, in a soda can. Those we can deal with gases in all those containers just dealing with pressure and temperature. But there's one item that we haven't considered, and that item happens to be the addition of gas or the removal of gas from the container itself. And we're actually going to deal with moles in this case, and so N is equal to the number of moles. And as we did earlier, we talked about how many moles of gas. If I have hydrogen, if I have 2 grams of hydrogen, I have 1 mole of gas, and of hydrogen gas. And so we're going to start to explore these moles. So first of all, what we need to do is consider the relationship between pressure and moles. So if I think about this, I'm going to look at, this is a comparison, pressure compared to moles. If you think about what's going on, if we add more moles, so if moles increases, what's going to happen to pressure? Well, as more things flood into the container, if temperature is held constant and the volume is held constant, then the pressure has to increase. It's kind of like putting more people in a classroom. If you already have 20 and you put 40 more, you're going to get an increase in pressure. And so if they both increase, then the equation for this is actually a constant times N. So what we have is pressure is equal to some constant times N. That's a direct relationship. And so we could write this again as pressure over moles is equal to some constant. Now, so those two are directly related. So let's look at volume now. And so if we start to compare volume to moles, as the number of moles increase, if we want to keep the pressure constant, we don't want it to go up, and we're keeping the temperature constant, then the volume has to increase also. So we have to give them a larger area to run around. So if they both go up, then we also have this thing that says that the volume is equal to some constant, and this is a different constant, times the number of moles. Or we can say that volume over N is equal to, you know what, we're going to add a little V on the bottom of that because we're talking about volume. We'll add a P up here because we're talking about constant related to pressure. Okay, so the next thing we need to consider, we've got pressure related to moles, we got volume related to moles. The one we don't have at this point is we don't have temperature. So let's compare our temperature. If we compare the number of moles, so we're going to start increasing the number of moles. We throw in some more moles. We want to keep the volume constant. We want to keep the pressure constant. So somehow those, even though we're adding more molecules, the atoms need to slow down so that they're not colliding as often with the side. In other words, increasing the pressure. Our volume's not going to increase, so just by adding moles, we would think it would increase in pressure. So we have to stop the number of collisions. So the only way to stop the number of collisions is to slow down the molecules. So we're going to decrease the temperature. And so if you look at that, as one goes up, the other one goes down. So that is what we call an inverse relationship, or we can write it as T is equal to the constant of temperature over the number of moles, or temperature times moles is equal to some constant. Okay, so right now we have basically these three equations of pressure related to moles, volume related to moles, temperature related to moles, and then we, on the end of the last video, we talked about that the pressure, volume, and temperature, we got this combined gas law. Well, in this case, we can kind of get a combined gas law relating to moles now. And so if we do that, what we end up with is we end up with this pressure times our volume divided by our temperature and our moles. And that's equal to a constant. And what we've found is that to find that constant is there's a guy by the name of Avogadro, and what Avogadro figured out is he said, if we have a gas at 1 atmosphere and we have that temperature at 273 Kelvin, which is 0 Celsius, which is what's called the standard state, and we have 1 mole of that gas. 1 mole of gas at standard conditions, 1 atmosphere and 273 degrees Celsius, occupies 22.4 liters. And by doing that, we're talking about an ideal gas, and this gas behaves in this method or ideal way. Now, what they figured out when they did this is they came up with this value of 0.0821. And if you look at the units of this thing, it's actually liters, atmospheres over moles Kelvin. And so what we have is that constant, or that value, is going to stay constant for this gas law. And so instead of using K, because we use K actually quite a bit, we came up with this thing called R. And R is called the ideal gas constant, and the ideal gas constant is 0.0821 liters times atmospheres over moles Kelvin. So what that reads really is 0.0821 liters if you have 1 atmosphere, 1 mole, and 1 Kelvin. And so what we're able to do is now use that, and we're able to actually get a new equation for our ideal gas law. And really, it says that the pressure times the volume is equal to the number of moles times this ideal gas constant times temperature. And so again, all we're looking for is each one of those variables to solve, either for moles, temperature, volume, or pressure. One of those variables is not going to be given. You're going to have to solve for the others. And if I look at my ideal gas constant, it tells me the units I have to be in. So if we look at 0.0821, that's liters. Then you have atmospheres for pressure. You have moles, and your temperature has to be in Kelvin. And so R gives away, what are those units that we have to have. Okay, so the ideal gas law is PV equals nRT. I always know it as PVnert. It kind of sticks in my head. All right. Now, using the gas laws, we actually start to look at what's called Dalton's partial pressure. And Dalton's partial pressure deals with all the gases in the container. And each gas in the container is going to exert a certain amount of pressure. And the total pressure of the container is the sum of all those different pressures. And so if I look at the problem that I gave you here, if oxygen and nitrogen are in a 2-liter container, it's just describing the container we have at 40 degrees Celsius, and the total pressure of the tank is 3 atmospheres. What is the pressure of each of the due to each of the gases? Well, if 20% of the moles in the container are oxygen and 80% of the moles in the container are nitrogen, then 20% of the pressure is going to be caused because of oxygen, and 80% of the pressure is going to be caused because of nitrogen. So the sum of those two pressures gives us that 3 atmospheres. And so what we can do in this particular case is to figure out how much pressure oxygen exerts is we're going to take 3 atmospheres and we're going to multiply it by 0.200. And so what we get is 0.60 atmospheres, and this 0.60 atmospheres is due to oxygen. So in that particular container, there's that much pressure caused because of oxygen. And so if we do the same thing for the nitrogen, we know that 0.800 is due to the nitrogen, and we get 2.40 atmospheres due to nitrogen. And hopefully those two numbers add up to give you the 3 atmospheres. So the total pressure of that system is the sum of the two separate pressures. Okay.